All right, welcome back. We are going to do this lesson, and it's called, it's 7.5, and it's called Congruent Triangles to the Rescue. And we're practicing. Practicing means that we've built up or developed our understanding. So now we're going to apply the things that we're learning. So it says, jumpstart. Previously, we conjectured about the opposite sides of a parallelogram being congruent based on experimentation and an explanation on rigid transformations. Based on this assumption, mark congruent segments in the diagram. So we're just going off of opposite sides being congruent. So go ahead and mark on your diagram. So I'm going to mark this congruent to this and this congruent to this. And it said, would drawing one of the diagonals of the parallelogram provided in problem 1 divide the parallelogram into two congruent triangles. Are those two triangles congruent? Are those two triangles congruent? That's what they're asking. What do you think? So in your head, you should be going over triangle congruence. Congruence, which is SSS, SAS, ASA, AAS. And I just write these down every time I'm trying to prove triangles congruent. So I already have I have two sets of sides. So I'm not going to use AAS or ASA. Okay. And then can you prove those two triangles are congruent? And the answer is yes. Okay. And we actually see that this third side, they share, right? So that is going to be our SSS. So usually when you have a figure like this, I always encourage my students to rewrite or draw the triangles separated out, because then you'll be able to see the side, and whatever else you're looking for. So I'm very used to looking at drawings like this. And so usually when my students get stuck, it's because there's a side or an angle or a something that they share that they're not really seeing. So it's always going to be beneficial for you to draw out those two triangles, something like this. And then you'll see that this is congruent to this and this is congruent to this. And you see that this side is congruent to itself. And in math, we call that the reflexive property. Reflexive reminds me of reflection, like a mirror. And so side AC is congruent to side AC. And so if so, yes, it's because of SSS. And name a pair of congruent angles in the diagram provided in problem 1. Now that we know that those triangles are congruent, we actually get all of those pieces being congruent. Remember, we talked about this. So once we prove that these two triangles are congruent by SSS, we actually get a lot of angles being congruent, right? And that's because the corresponding parts of congruent triangles are congruent. Okay, so that's answer 4 and that's answer 5. So you can name any angle that you want. I'm going to name angle D is congruent to angle B. And that's because of CPCTC. Again, corresponding parts of congruent triangles are congruent. You're going to hear me say that a lot. Okay, so today our focus is going to be to identify congruent triangles and then write congruency statements. Remember, we talked about this when we have the triangle ABC is congruent to triangle DEF, something like this. And remember, we talked about a picture's worth 1,000 words, and all those statements that we get are congruent once we say that. We'll be practicing that today. It says, we'll also be able to use triangle congruence to justify other properties of geometric figures. How can I capture what I see when I identify congruent triangles in symbolic notation? How do I use the triangle congruence criteria to justify other properties of geometric figures? And when might it be helpful to decompose a geometric figure into triangles so that I can use triangle congruence criteria to prove something else about the figure? All right, so Zach and Sion are exploring isosceles triangles, triangles in which two sides are congruent. Zach, I think every isosceles triangle has a line of symmetry that passes excuse me, through the vertex of the angle made up by the two congruent sides and the midpoint of the third side. I'm just going to show you a picture of what he's saying. So an isosceles triangle is when you have two sides congruent. Zach says this is a line of symmetry for every isosceles triangle. Okay. That's a pretty big claim, Sion says, to say that you know something about every isosceles triangle. Maybe you just haven't thought about the ones which the claim isn't true. Zach, but I folded lots of isosceles triangles in half and it always seems to work. Sion, lots of isosceles triangles are not all isosceles triangles, so I'm still not sure. Number one, what do you think about Zach's claim? Do you think that every isosceles triangle has a line of symmetry? If so, what convinces you that this is true? If not, what concerns do you have about this statement? Okay, so go ahead and think about that. Excuse me. All right. So so maybe some of you are like, yeah, I agree with him. He's folded a bunch of them, so it must be true. So that's okay, but in math, when you make a claim like I think every isosceles triangle has a line of symmetry, this right here, and you haven't checked all the cases, it's only true for the ones that you've checked. Does that make sense? So in math, in order for you to make a statement about every isosceles triangle, you have to go through all of them. And let me just tell you, you can't go through all of them because there's an infinite amount. Okay. So he's basically doing a proof based on experimentation, which is not a valid proof method. Okay. Just because I flipped the coin and it landed on heads the first time doesn't mean that the next time I flip it, it's going to land on heads, right? So the experiment told me that it's going to land on heads 3 times in a row. That means that it must be heads every single time. That's not a valid claim, right? And you kind of know that. All right, what else would Zach need to know about the crease line in order to know that the line is a line of symmetry? Hint, think about the definition of a line of reflection. So, what else would Zach need to know about this line to prove that it was true? And they said, hint, think about the line of reflection. So, if you remember from our last section, or a couple sections ago, when we were talking about reflections, there was something interesting about, like, let's just say this point here and this point here. And when I connected those two lines and the line of reflection. And so if you remember, these two lines had to be perpendicular. They had to be perpendicular. Okay, let's move on. So it says, Sion thinks that Zach's crease line, the line formed by folding the isosceles triangle in half, creates two congruent triangles inside the isosceles triangle, which criterion ASA, SAS, or SSS could he use to prove and support this claim? Describe the sides and angles that you are saying are congruent and explain how you know they're congruent. Okay, so let me draw this again. Here's my triangle. Are these two triangles congruent? Are these two triangles congruent? So for sure, I have a side and a side, and then I have they share a side, right? And because he keeps folding this and this is a line of reflection, we know that this side is congruent to this side. So how do you talk about those two triangles? Those two triangles are congruent by which one? Very good. SSS. Excuse me. Okay. Number 4, it says if the two triangles created by folding an isosceles triangle in half are congruent, what does that imply about the base angles of an isosceles triangle, the two angles that are formed by the two congruent sides? So they're asking about these two angles here and here. What does that imply? Well, it implies that they are congruent, right? The reason why they have to be congruent is because we've just proved that the triangles are congruent. So therefore the angles are congruent. And this is a theorem, right? And I'll write it like this. Base angles of an isosceles triangle are congruent. So this is a theorem that you guys just proved. You just proved that, right? So it says number 5, if the two triangles created by folding an isosceles triangle in half are congruent, what does that imply about the crease line? You might be able to make a couple claims about this one. One comes from focusing on where the line meets the third non-congruent side of the triangle. A second claim comes from focusing on where the line intersects the vertex. Okay. So there's a couple of true statements we can make about this. Okay. And I'll say it like this. Now, number 1, we know that it's perpendicular. Number 2, we know that it bisects because we have a congruent part and a congruent part here. But we also know that this angle is congruent to this angle. So we know actually a lot of things, okay? Because we proved that those two triangles are congruent. And because those two triangles are congruent, we get that line of reflection is perpendicular to the base, and it bisects the base, and it also bisects that vertex angle. Okay. Part 2. Like Zach, you have done some experimenting with lines of symmetry as well as rotational symmetry. In this task, you did in the task you did in symmetries of quadrilaterals and quadrilaterals, beyond definition, you made some observation about sides, angles, diagonals of various types of quadrilaterals based on your experiments and knowledge about transformations. Many of these observations can be further justified by looking for congruent triangles and their corresponding parts. So what are you going to be doing? You're going to be looking for congruent triangles. Just as Zach and Sion did in their work with isosceles triangles. Pick one of the following quadrilaterals to explore: a rhombus, a rectangle, or square. A rhombus is a quadrilateral where all sides are congruent. A rectangle is a quadrilateral whose angles are all congruent. And a square is both a rectangle and a rhombus where all sides are congruent and all angles are congruent. So draw an example of your selected quadrant. So this is the part where you guys are going to explore on your own, and we're going to come back together and learn about all these pieces, okay? So they want you to draw your quadrilateral. So you pick one, label the vertices with A, B, C, D, and label the point of intersection of the two diagonals as N. So then they want you to look at that. So go ahead and do that. So based on your drawing and the given definition of your quadrilateral and the information about the sides and angles that you gather based on lines of reflection and rotational symmetry, list as many pairs of congruent triangles as you can find. Now, here's where your skill comes in. You should be using ASA, SAS, SSS, AAS, right? So it says for each pair of congruent sides that you list, state the criterion you used, all those, to determine which that the two triangles are congruent, and explain how you know that the angles or sides are congruent. Okay, so now it says for each pair of congruent triangles that you list, state the criterion. Okay, we did that. So now what you're going to do is you're going to fill all this in. Okay. So we're going to talk about all of these different things that you all learned here. So this could be your chart for congruent triangles. This might have more space than you actually need for your particular one. And then we're all going to come together and talk about what we learned so that way you know what to do next. So thank you for listening and have a great day.